continuing series of videos on the unification of physics. This is where we left off last time. We're about done with the journey. We're almost there. We discussed in previous videos the classical physics. Remember Newtonian mechanics with the concepts of space-time and matter. Really the first modern physics theory, which was put forward by Isaac Newton. Maxwell developed his theory of electromagnetism in the 1800s. It was a field theory. And Einstein removed the contradictions between Newton's theory and Maxwell's theory by unifying space with time through his special theory of relativity. However, it only applied to inertial reference frames. And then about 10 years after the special theory of relativity was created, Einstein created his general theory of relativity, and it's our current theory of gravity. It's also a field theory. Quantum mechanics was a reaction to the inability of classical physics to accurately describe physics on small scales. Quantum physics went through a number of iterations over time. The first theory was put forward by Schrödinger and Heisenberg. It was called non-relativistic quantum mechanics. It filled in some of the holes that were left by classical physics in explaining the physics on small scales. It had a few limitations, as we discussed before. It was replaced by Dirac's theory, which was called relativistic quantum mechanics. It was a unification of special relativity and non-relativistic quantum mechanics. When Dirac unified those two things, that explained the spin characteristics of elementary particles. And it was a much improvement over the non-relativistic quantum mechanics. Non-relativistic quantum mechanics was three-dimensional. Dirac's theory was four-dimensional. It only applied to inertial reference frames. There was this issue of the quantum vacuum, where Dirac conceived this infinite vacuum state filled with negative energy electrons that allowed positive energy electrons to exist. It was unmeasurable and undetectable, so some physicists felt that was an anomaly and needed to be improved upon. Dirac's theory basically only covered the theory of electrons. There were no theories really that addressed what went on in the nucleus of an atom, and that was remedied somewhat by the discovery of the neutron. And the discovery of the neutron gave an explanation for why elements had different sizes. The Yukawa theory, as you remember, explained how the nucleus of an atom stayed together, didn't blow apart. There was a nuclear force inside the nucleus that held the protons and neutrons together. They exchanged a particle called a meson. Those exchanges created an attractive force. Radioactivity was explained by three different theories, alpha, beta, and gamma decay. They gave an explanation for why the nucleus didn't grow infinitely large. In this video, we're going to take the last step and talk about the Standard Model, which has three theories: electrodynamics, the weak interaction, the strong interaction. Sometimes those are called sectors of the Standard Model. Describes the physics on the small scale. General relativity describes the physics on the large scale. And what we'd like to do in the 21st century is to unite them into one consistent theory. Those two theories are incompatible, as we know. The goal in 21st century physics is to try to find some way of uniting them into one theory, and we usually call that theory quantum gravity. The theory of quantum gravity doesn't exist yet, but that's what we call the unification of physics. The Standard Model is not a completely predictive theory, whereas general relativity is. It doesn't need to be supplemented by anything external to it to make its predictions. In that sense, it's a wholly predictive theory. The Standard Model is not a wholly predictive theory. It does have a theoretical part. The theoretical part is called QFT, quantum field theory, and we'll talk a little bit about it today. But it needs support from external inputs before the model can make its predictions. One of those is 19 or so adjustable constants that have to be set before the model can be run. The adjustable constants are the masses of some of the particles and other things. It's not too important that we know much about that. Just be aware that that exists. The 19 or so adjustable constants are just that, they're adjustable. So depending on the energy levels of interest, the constants have to be adjusted before we run the model. And if you hear physicists refer to something called fine-tuning or something called the hierarchy problem within quantum mechanics, that's usually what they're referring to, because we don't know theoretically why the constants have the values they do. These are inputs to the model that need to be set before we can run the model. Another thing that we need to do is include something called the Higgs mechanism. The Higgs mechanism tells us how particles gain mass. All the particles in quantum field theory are massless particles. So there has to be something in the theory that allows us to explain how particles gain mass, and that's called the Higgs mechanism. And the fourth thing that needs to be added to the standard model before it can make predictions is something called renormalization. Renormalization is basically a mathematical concept. Some of the functions that the standard model uses or that quantum field theory uses are quite complex, and so some of these functions are estimated or approximated by simpler functions that make the calculations easier, basically a series of simpler functions, but normally the number of terms in those series is infinite. And that doesn't always cause a problem because some of the sums converge to a finite number. We can deal with it that way, but that doesn't always happen. Sometimes the series of functions adds up to infinity, and when it does that, we have to use what is called renormalization to get rid of the infinities. In a previous video, I discussed renormalization in much more detail. If you want more information about renormalization, you should go to my books on the website and you can read more about it. With that, we'll talk about the standard model. So the key to creating a theory of elementary particles came through the idea of symmetry. There was an algebraist, her name was Emmy Noether. She created Noether's theorem, and it was a very important theorem, maybe the most important theorem. And what her theorem said was that all continuous symmetries were associated with a conservation law. And physicists had formulated many conservation laws that seemed to hold in nuclear reactions. They had written them down. There was conservation of angular momentum, conservation of linear momentum, conservation of energy, conservation of electric charge, and so on, all different kinds here. And what Noether's theorem did was to show for each conservation law, you could write down a mathematical construct that would describe the conservation law. Mathematicians study symmetry under the title group theory. A group is an algebra. So what's an algebra? Well, let's suppose that you have a set of elements, and I'll just write something like S is equal to A, B, C, some set of elements, and what we call a correspondence rule, and I'll just write that like that. And those combinations, a set of elements and a correspondence rule, produces an algebraic structure. If you correspond any element in this set with any other element in the set, something like that, that correspondence gives you another element in the set. If that rule holds, that's called an algebra. That rule that we just described is called closure. Group theory is an algebra. All groups have closure. But groups have three other rules that have to hold if the structure of a set with a correspondence rule is to be considered a group. So one of the other rules is called associativity. When we correspond to something like this, that correspondence there is unambiguous because each of the two possible ways you could correspond are equal. There's no confusion between this correspondence rule. And all groups have associativity as a rule. The third rule is identity. There is some unique element in this set that when you correspond it to any other element, it gives that element back. For example, let's say that E is the identity element. Then if we correspond A with E, that's going to give us back A. Or any other element, if this was a B and corresponded with E, it would give us back B. It also commutes, which if we did this, corresponded to A, we would get A back. Or any other element. So the set must have an identity element. And correspondence rules can be mathematical operations like addition and multiplication, but they don't have to be. They can be something else, and we'll look at an example. Now, the last rule that's required to make a group is an inverse. So what that says is if we take any element, there's another element that gives us the identity element back. Every element in the group, there's a unique element within that group, such when you correspond them, you get the identity element. And if all four of those rules hold, then the algebraic structure is called a group. Well, let's look at a couple of examples. Suppose we have the set W, and I'll just make that set 0, 1, 2, 3, and so on. And I'm going to make the correspondence rule addition. And we want to ask the question, does that structure constitute a group? So let's see. We'll call this set the whole numbers. If we add any two whole numbers together, do we get a whole number? And the answer is yes. Closure is satisfied. If we associate, if we do something like this, 1 plus 2 plus 3 is this equal to 1 plus 2 plus 3. That's the associative law. This would be equal to this. Associativity is satisfied. Is there an identity element within our set here, an additive identity? And the answer is yes. If we take any of these elements, say we take 2, and we add it to the identity is 0, we get 2 back. And that's true for all the elements. So 0 is our additive identity. Identity is satisfied. But what about inverse? And what that tells us is we have to take any element in here. We'll take an element 2, and we have to add that to some other element, and we have to get 0. Can we find an element in our set that makes this true? And the answer is no. If we wanted to get this, we would have to have a minus 2. If we added 2 to a minus 2, we get 0, but we don't have a minus 2 in our set. So the inverse requirement fails. We say that whole numbers with the correspondence rule addition does not form a group. It is not an algebraic group. All right, so let's see if we can figure out how we could make an algebraic group. Well, let's try another set here, and this set would be the integers. So that would be minus 3, minus 2, minus 1, 0, 1, 2, and so on. Dot, 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 dot. Well, I'm running out of room here. And the correspondence rule would be plus. All right, so we could ask the question, does that set with correspondence rule addition form a group? Well, it's pretty clear that closure is satisfied. If we add any of these two numbers up, we're going to get another number in the set, so closure is good. Associativity is good. The identity element is again 0. If we take any element out of this set and add 0 to it, we get the element back. So the identity element is 0. It's in here. We're good. Now, what about the inverse? This time, we succeed. If we pick any element, we'll pick the element 3. And if we add minus 3 to that, we're going to get 0. That satisfies the inverse property. The integers, under the correspondence rule, addition forms a group. Now you can kind of get an intuitive idea about that if we look at the W set, the first one we did, and look at sort of this is the 0 point here, and then we would have 1, 2, 1, 2, 3, on down, you notice it's kind of lopsided. All the numbers are on one side of this, well, I'll call it a symmetry axis. But when we look at the integers, this set with correspondence rule, we would get, this would still be the 0 point. This would be 1, 2, 3 on down. But then over on this side, we would get -1, -2, and -3, so on down. And you can see that there is a kind of a balance here. One side of this axis looks just like the other side, like it's in a mirror. And so you get this kind of idea of symmetry in that sense, where it's kind of a balance, and you can kind of see intuitively how this works. For example, if you have a teeter-totter and you put a 100-pound weight over here and a 100-pound weight over here and over here, you get a balance, and that has a kind of a symmetry. If you put tables that look just alike on both ends of your couches, you kind of have a sense of symmetry. Group theory in mathematics is trying to formalize that concept of symmetry. That's why they call group theory the mathematics of symmetry. Let's look at an example that doesn't involve a mathematical operation. We're going to look at the permutation group. If you have a set of n distinct objects, and n is a whole number, it can be 10 or 100 or whatever it is, the number of ways that you can arrange those objects, how you can order them, is n factorial. N factorial is defined as n times n minus 1 times n minus 2, all the way down to 1. And we just keep subtracting 1 from n until we reach 1. And we multiply those numbers all together. We get the number of ways that we can arrange n distinct objects. We're going to set n equal to 3. So the number of ways that we can arrange 3 objects is 3 factorial, but that's 3 times 2 times 1. That is 6 ways. The 6 ways are listed here. If we look at the first way, this E, you might surmise that that might be the identity element, and you'd be right. And what it tells us to do is nothing. If we have an arrangement like that, we put the first element in the first slot, the second element in the second slot, and the third element in the third slot. So we don't do anything. Another thing we could do is, if we had this arrangement to start out with, we could just we would just switch 1 and 2. B, we could take this arrangement and switch 2 and 3. C, we can just switch 1 and 3, the first element and the third element, and so we get the arrangement 3, 2, 1. And D, we just move the numbers over by 1. So we put 1 over in the second slot, 2 in the third slot, and 3 in the first slot, and we get D. For F, we can just move the numbers 2 slots over. And so that gives us all the permutations that we could possibly make from 3 distinct objects. There are 6 of them. It turns out that the permutation is a correspondence rule. Here we have the set 1, 2, 3, and a correspondence symbol, I don't know, I'll call it a permutation, P. This set with this permutation being the correspondence rule creates a group. Now, let's see, we better check that and make sure that that's true. The first thing we have to check is closure. If we take E, we act on it and we arrange it according to A, we would switch the first and second elements. And then if we were to take A and permutate it like B, we would just switch the next 2 elements. And so we would get 2, 3, 1. Well, 2, 3, 1 is F. Now we could do it the other way. Suppose we started with B, we changed E into B, we switched the third and second element, and then we would permutate it according to A. And it tells us to switch the first and second element. So we would get 3, 1, 2. But 3, 1, 2 is D. And so you can go through all these and do as many as you want. But the bottom line is that anytime we permutate any of these elements, however many times, we're always going to get another element in the set. In this set here, mathematically, the permutations are closed. We never get a permutation that isn't listed here. We could also show associativity. It's hard to do. It's labor intensive, so I won't show it. But we can say that this permutation group does follow associativity. What about the identity element? Well, I've already kind of told you that. It's E. And E, what does E do? It doesn't do anything. It doesn't permutate the objects at all. It just leaves them alone. If we start out with A and we permutate it with E, we just leave it alone. And so it's just A. We could write A, E is going to get us A. And any of these other permutations, we could do B, E is equal to B. The identity element for this group is E. Now, what about the inverse? Well, let's see. It turns out that each of these permutations is its own inverse. So if we do A, we would get E. B, B, we would get E. And you can see that in the chart here if you go down the diagonal here. And so we can check that if we want to. Take A, and we put the second element in the first slot and the first element in the second slot, just to switch the first two elements. If we apply A again, it would just tell us to switch the first two elements. So we put 1 here and 2 here. That would give us 1, 2, 3. Well, 1, 2, 3 is the identity element. Let's try B. Well, B tells us to switch the second and third elements around. If we do that again, we get 1, 2, 3. 2 goes there, 3 goes back there. And that's 1, 2, 3. And you can go all the way through each element and show that C is equal to E, and so on. Now, one way we can formalize this is to write something like this. So I know that F, and we'll put that, and we'll call that the final state. And then we'll put B, A, and then we'll put E here and call that the initial state. And so that's a way that we can formalize this whole idea of a permutation group. You can think of B and A and B, as operators. Operators. And they operate on states, on these first states, and they permutate or change the state into something else. So if A operates on E, well, what does that give us? Well, we know what that gives us. It gives us A. We could write F, B. This would become A. If B acts on A, that tells us to switch the second and third element around. So we would get 2, 3, 1. Well, 2, 3, 1 is F. So we can write something like that. And so we have reached the final state. After we've operated with these two operators on the initial state, we could write this in general as having a final state. I'll just use a capital F so we don't confuse it with that. And then we would have some operators in here. We'll just put, which are other ones of these, put in here. And then we could write the initial state like this. And that's the way we could formalize this permutation group. This operator would act on the initial state, permutating it, then we would permutate it again and reach a final state. And we could do that with any number of these. And this would be an initial state here. These would be called the operators, and these would be called the states. When this operator acted on this state, whether it's any one of these, it would permutate it, and we would just keep operating on it with each operator until we reached the final state. And that's sort of a formalization of these permutation rules. And the reason that I'm telling you this is that this is very similar to the way things are done in quantum field theory. This is how it sort of works. So let's do another one. Suppose we just switch these. So I think the state's going to be, the final state's going to be, D, and I'm going to switch these around. I'm going to put B operates first on E. So we've just switched them around. If we operate on E, well, we know what that is. That gives us D, A here, that's going to change it into B. We know that from here. B operating on E gives B back, so we have state B. What happens if A acts on B? Well, here's B, and A tells us to switch the first two elements around. So we're going to have to switch 3 and 1. So we're going to get 3, 1, 2. But 3, 1, 2 is D. We would have D. And so you can see that we reach a final state there, and that's sort of looks like that, except our final state was D instead of F. And all we did was switch around the order in which the operators operate. I should mention, just as passing, that a group is a non-abelian group. If these were numbers, if we were multiplying, A times B would be equal to B times A. But in this case, when we change the order of the operation, it doesn't give us the same answer. It's called a non-abelian group. This is kind of abstract. A reasonable question would be, if this is a group, what is it a group of? It's a symmetry of some kind. What is it a symmetry of? Well, it turns out that permutation group is a symmetry of an equilateral triangle. You have to kind of remember what an equilateral triangle is. It's a triangle where all the sides are equal and the angles are equal. 60 degrees, 60 degrees, 60 degrees, and whatever. We can just say these sides are 1. If you look, here's E. We have 1, 2, 3. And if we interchange the 1 and the 2, that's A. We just flip it around the symmetry axis here. And if I were to do that, and your back was turned and you didn't see me do that, and I took these numbers off, you wouldn't be able to tell that I'd done anything. The equilateral triangle would look the same after the operation as it did before. The same with B. All I do is switch 2 with 3, and that's just flipping this around this symmetry axis here. And that makes B. If I flip it around this symmetry axis, I'm just interchanging 3 with 1, and that's C. And those are all the symmetry operations of an equilateral triangle. So when I do those operations, the orientation of the triangle is conserved. Unless I numbered them, you wouldn't be able to see that I had done anything. Of course, the symmetry operations that you see in the standard model are much more complicated than these, but the same idea. That something, when it gets transformed from an initial state into a final state, something about that interaction or that process doesn't change. And that was the key to formulating a theory of elementary particles. And so let's take a quick look at the standard model. Now, in quantum field theory, fields are fundamental, particles are secondary. So fields interact and they create and destroy particles. So fields permeate the entire space. When they interact, they either create or destroy particles. That's called quantization. That's sort of the basic concept behind the standard model. Each particle has a field associated with it, and when you quantize that field, it creates a particle. This is a snapshot of the standard model particle classification scheme. These are all the particles that exist that we know about. It replaces the periodic table of the elements. We can go from here to here if we want to, but there's far fewer elements in the standard model than there is in the periodic table of the elements. And so there's two kinds of particles. There are the fermions, and they're shown over here. These are fermions. And then the gauge bosons are lined up here. Those are the force-carrying particles. This particle here is called the Higgs. We talked about it a little bit. It's a boson responsible for giving particles mass, as we've said. And those are all the particles that we know about in nature. The particles in the green box are called leptons, and they're free particles. You can see them in laboratories and particle accelerators and things like that. On the top here are the quarks in the purple, and there are 6 of them. They are not free particles. They're held together by something called a gluon, and they come in either triplets or doublets. They're never found in isolation. So, for example, you don't see a proton or a neutron listed in our particle classification scheme. A proton is made up of quarks. You can see it over here. A proton is 2 up quarks and a down quark. A neutron, which we don't see over here either, is made up of 2 down quarks and an up quark. And there are a bunch of other particles that we can actually see in particle accelerators. And so all the fermions come in these triplets. They're made up of the quarks, and the quarks you can never find them in isolation. We can make a boson out of 2 fermions. In fact, the mesons, you don't see mesons in the particle classification scheme either. If you put a quark and an anti-quark together, you create a boson. And you can see some mesons here that are a combination of quarks and antiquarks. We'll talk a little bit about the force-carrying particles. They're usually called mediating particles. The photon is a mediating particle for all electromagnetic interactions. The W and Z bosons are the mediating particles for the weak interaction, and the gluons are the mediating particles for the strong interaction, what holds the nucleus together. Those are all the particles that we know about in nature so far. So here's the role that quantum field theory plays in the standard model. If you remember, we did a permutation exercise where we called these operators. They acted on what we called states, and this was, if you remember, this is E. A acts on E and becomes 2, 1, 3, and then we'd have a B, and that would become A. A is 2, 1, 3. B acts on A, and that gives us F. B acts on A gives us 2, 3, 1. If you remember that, sort of how you could think of formalizing the permutations in permutation group. And the reason I showed you that is very similar. It's not the same, but it's very similar to the way that quantum field theory works. And I'll give you an example. So what we are after in quantum field theory is something called a transition amplitude. All your quantum calculations aim at calculating a transition amplitude. Any quantum system that's found in an initial state, it's acted on by field operators that create and annihilate particles. The I is an initial state of particles. The field operators operate on the particles and change it into the final state, which we've written as F. And so it's very similar. The process is very similar. Of course, we're dealing with the symmetries of an equilateral triangle here. We're dealing with other symmetries here, and I'll talk a little bit about that in a minute. We can look at this particular interaction over here, and this is a very simple one. There's lots more complicated ones that you can do, but a simple one will suffice here to illustrate how this works. In the initial state here, we have an electron and a positron. There will be 2 operators that operate on the electron and the positron, annihilate them, and then create a photon, which is a boson. At another position in space, they recreate the electron and the positron. That's a very simple scattering type of interaction, but it's one that happens. So what I've done here is I've taken these operators and written them in a more descriptive way, right here. In quantum field theory, we take these annihilation operators, which I've written here and here, and what they do is they act on the initial state and annihilate the electron and the positron. And they give us the vacuum state, where there are no particles. The particles have been annihilated. Along with that, you have this K2 factor that comes out of the formal mathematics of quantum field theory. It's not important that we understand what it is. It's just a number. Again, we can kind of ignore it for now, but it's important when we get along in the process. Now, this creation operator creates a photon. So it creates a virtual photon, which is a boson. It's a gauge boson that mediates all electric interactions. This creation operator for the boson, once it creates a boson, We get a number with it that comes out of the formal mathematics of quantum field theory, and we just designate it as case sub gamma, just as a placeholder. At x2 at position, or sorry, x1 at position x1, this destruction or annihilation operator annihilates the photon. These two creation operators create an electron and a positron. They are replaced by this K1 here, and these are all numbers. We can factor these numbers out of the bracket, and the transition amplitude just comes out to be these three numbers, whatever they turn out to be. And then this inner product here is always defined to be 1 in quantum field theory. The transition amplitude comes out to be these three numbers, and these three numbers come down. The square of this transition amplitude is equal to the probability that this interaction takes place. That's where the probabilities come in. And that, in a very oversimplified nutshell, is the way quantum field theory works. All works like this. Some of the transitions and interactions are very much more complicated than what we've looked at here, but the high-level process is the same. In all of these transitions, we start out with an initial state, we operate on the initial state, it gets transformed through all these operators into a final state, and once we've done all that, the mathematics tells us the square of this transition amplitude is the result. The square of that number tells us the probability that that particular interaction happens. And that is, in an oversimplified nutshell, the essence of quantum field theory. So the standard model consists of three gauge theories: quantum electrodynamics, quantum flavor dynamics, and quantum chromodynamics. QED deals with electromagnetic interactions. QFD deals with nuclear decay or weak interactions here. QCD deals with strong interactions or how the nucleus stays together. Well, why are they gauge theories? What does that mean? It means that they're governed by the symmetry, basically, conservation law. So whatever equations are written down to describe the electromagnetic interactions of particles, those equations have to have a U1 symmetry. That's how you write it down. And in any electromagnetic interaction, electric charge has to be conserved. It can't change. So we can have something like this. We studied this before, where an electron and a positron annihilate, creating a virtual photon, and then they're scattered like this. And in any electromagnetic interaction, electric charge has to be conserved. So you can have a bunch of particles coming in, being annihilated, creating a virtual photon, and then less or more particles coming out the other side. But if you add up the electric charges of those particles and add up the electric charge on those particles, they have to be equal. They can't change. And that's what the symmetry is in the theory of quantum electrodynamics. Quantum flavor symmetry deals with nuclear decay, and what is conserved is something called weak isospin. That's an SU2 symmetry. That 2 does mean something. Each particle is assigned a weak isospin number, and it can only have two possible values. Over here, it can be plus 1/2 or minus 1/2. And if we look in this chart, I don't know if you can see this, you probably can't, but the electron has a weak isospin of minus 1/2, the neutrino plus 1/2, the up quark plus 1/2, and the down quark minus 1/2. In all weak interactions or nuclear decays, all the equations that describe those type of interactions must conserve weak isospin. If we look at an example here, this is just a Feynman diagram of beta decay. Beta decay. If a neutron is converted into a proton, in that decay, there's an emission from the nucleus of an electron and an antineutrino. And so we can ask the question, is weak isospin conserved in that interaction? The neutron has an up quark and two down quarks. Well, up quark is plus 1/2, and a down quark is minus 1/2. And another minus 1/2. So the total here is minus 1/2. A neutron has weak isospin of -1/2. If we do the same thing up here, up quark +1/2, up quark +1/2, minus quark -1/2, that's a total isospin of 1/2, +1/2. And if we add these two up, we get 0. So the total weak isospin before the interaction is 0. And then the transmutation occurs, and it creates an electron and a antineutrino. Well, the antineutrino has a +1/2, and the electron is -1/2, weak isospin. If we add them up, it's 0. And so you can see that in that interaction, weak isospin is conserved. It's what's conserved in all nuclear decays. That's usually called quantum flavor dynamics. Quarks come in flavors: up, down, charm, strange, top, bottom. And we saw that in the standard model classification chart for particles. Now, so those are called different flavors. Again, what's conserved in all weak interactions, this is a very simple one, is something called weak isospin, and it's an SU2 symmetry. Okay, so that brings us to the nucleus of the atom, or the strong interaction. And what's conserved there is something called SU3, where that's the symmetry. And what is conserved physically is something called color charge. Let's take an example. Suppose there's a particle U. Now there's a particle like that. I don't even remember what it is, but there's a particle like that. But we have to remember, that's 3 up quarks, by the way. Quarks are fermions, and fermions cannot be in the same state at the same time. That's a violation of Pauli exclusion principle. Something else has to be added to ensure that these particles, or these quarks, don't occupy the same state. They're fermions, so they can't occupy the same state at the same time. So they're given labels. This would be a red up quark, and a green up quark, and maybe a blue up quark. And that allows these quarks to be different. They have different color charge. Color charge has to be conserved in all strong interactions. A combination of red, green, and blue, and any of those combinations, is called white. For example, within the nucleus, if we change a neutron into a proton, the flavors of the quarks can change, but the colors can't. We have to have a red down quark, a blue down quark, and a green up quark. And then we can, back over here, we have to have the same thing. Red down quark, a green up quark, and a blue up quark. That color charge has to stay the same. The mediating particle in the strong interaction is the gluons. That's what holds the quarks together. And a gluon is an antiquark and a quark pair. That's a boson. Since the symmetry is 3, you might guess that since there's 2 of these, we take 2 and raise it to 2 to the 3rd power. That would give us 8. And so you might surmise that there are 8 gluons. And there is. If you were to guess that, there is. I'm not sure that's the way you should calculate that. They do it different in the theory of gluons, but we'll ignore the mathematical faux pas here. But there are 8 gluons. And the thing about gluons is they participate in the strong interaction. You can transform gluons into other gluons. It's all predicated upon this symmetry. What's conserved in strong interactions is color charge. Doesn't change. So that's basically, in a very, very high-level, oversimplified nutshell, the 3 sectors of the standard model. The symmetries dictate what particle interactions can take place in natures and which ones can't. And that's the beauty of the standard model. We've pretty much arrived at where we wanted to get. We've talked about classical physics, Newtonian mechanics, Maxwell's theory of electromagnetism. We saw how Einstein's special theory of relativity was able to remove the contradictions between Newtonian mechanics and Maxwell's theory through uniting space with time. It only applied to inertial reference frames. And then we found in this video something interesting, that the theory of electromagnetism has become a quantum theory. Almost everything that was in here is now in here. And the reason for that In classical physics, in order to handle electromagnetism adequately, the electric current should be fundamental. And that's a nice, smooth, continuous substance that could be described classically. But it turned out that it was the motion of electric charges that created an electric current. It was the charges that were fundamental, not the current. And a charge is sort of a quantum idea. So we have to move electromagnetism over to the quantum side of the ledger. So that doesn't exist on that side of the ledger anymore. What is important on this side of the ledger is the general theory of relativity, which improves upon Newton's theory of gravity. And it's a field theory, and so we're just left with general relativity and the special theory of relativity on this side. We've gone through the progression of quantum physics, started out with non-relativistic quantum mechanics, and then moved on to relativistic quantum mechanics in Dirac's theory, and ultimately we reached the Standard Model today. So we're sort of finished. And the Standard Model has three theories. They're governed by different symmetries. This one is U1, remember. This one's SU2. This one's SU3. These symmetries are basically associated with conservation laws, and they do that through Nader's theorem, as you remember. We would like to unify this side of the ledger with this side. And one of the steps that needs to be taken is to unify these three theories into one theory, because they're all governed by different symmetries. There's a lot of work in physics today that tries to use multiple dimensions. If we have to add up these dimensions in order to unify these three theories together, we're going to have a higher dimensional theory. And these are not the same symmetries. So one of the challenges is, how do you unify these three theories into one? And those are generally called grand unified theories, or GUTS for short. There's lots of them out there. GUT theories that try to unify these three gauge theories in the Standard Model together. None of them are generally accepted in the physics community today. These haven't been unified in any sense, but that's one of the challenges that needs to be accomplished before we try to unify this side with this side. We're going to have a video talk a little bit more about grand unified theories. All right, we've arrived. We've finished, basically. We're where we wanted to go. We've talked about the theory of relativity. It's our theory of gravity and the theory of large-scale physics. And we've talked about the quantum physics. Again, we haven't talked much about unifying these three theories into a GUT, but we've talked about how these three theories are governed by different symmetries. This is a U1 symmetry. This is a SU2 symmetry, and this is an SU3 symmetry. And these symmetries are all associated with conservation laws, but they're not the same symmetries. The challenge is, well, how do you take these three different theories, which are governed by different symmetries, combine them into one, and make a higher dimensional theory? One of the biggest problems in trying to do that is that U1 is an abelian group. It's commutative, and U2 and U3 aren't. From a physics standpoint, the difficulty here is the gauge boson that mediates the quantum electrodynamic theory is a massless particle. The W and Z bosons that mediate the weak interactions have masses, so we have to understand why the mediating particle for the electrodynamic part of the Standard Model is massless, and why these have masses, and why the gluons don't have masses. The gluons are massless particles, but they're confined. Certainly the particles that they represent have masses. There's some problems within the Standard Model that the calculations of the masses aren't quite what you'd want them to be, and so there has to be an explanation for that. Also, the gluons can transmute into other gluons, so they participate in the strong interaction. But none of the other bosons, the W and Z bosons or the photon, can create other photons or other W and Z bosons. They don't transmute, but the gluons do. the mediating particle for the strong interaction transmutes into other mediating particles, and that doesn't happen in either of these two interactions. W bosons don't turn into Z bosons and vice versa. That doesn't happen, and photons don't create other photons. It only happens in the gluon case. And those are great challenges for physicists to try to figure out how you unite these three theories into one theory and then explain why these mediating particles are so different. So there you go. We're going to have another video, one more, that's going to talk about some efforts to try to go beyond the standard model and try to unify those three. The whole idea of this is to try, at some point, to unite the theory of relativity with the standard model. The foundations under which the two theories are developed are different. They're incompatible, and we have to find some way to unify them into a quantum theory of gravity. That's what we call it. It doesn't exist yet, but that's what we call the unification of physics. So if you want to know about the efforts to go beyond the standard model, please tune in.